Welcome to Lesson 1-1. Here is your video podcast. We'll start off with your little math problem of the day. Take a look at this one. It's kind of fun. Next, your math thought of the day. Enjoy. And now we'll start off with Lesson 1-1, recursively defined sequences. We'll talk about that word recursive, and we'll talk about what is a sequence, and we'll start talking about how do you write formulas for certain sequences. Now, sequences and all these recursive formulas we're going to talk about today are all centered around patterns. Okay. Now the top three are different patterns that occur in nature. Notice these patterns are geometric patterns. And notice the shapes on the bottom are things you may recognize. They are known as fractals. They are also types of geometric patterns. We'll talk about Sierpinski's triangle in a little bit. But Koch's snowflake here is this kind of shape. But notice what I want you to notice is there's different iterations of Koch's triangle. The top one, is probably one of the simpler iterations, and it's only a portion of it. But notice how you get the second iteration and the third iteration. You take each line segment, break it up into thirds. You take that middle third and make it into another little triangle. Okay, and if you continue doing that, so notice we did that to go from the first to the second and the second to the third, you get what's known as Koch's snowflake. Now again, these are very geometric patterns. What we're going to focus on, our formulas today are mostly going to be numeric though. We use patterns all the time. For instance, when you talk about different types of architecture, you always see patterns there. And if you basically take different crystal structures and you break them down, you'll definitely see geometric patterns there. Now, we're going to talk about some different terminology that goes along with these patterns. First of all, when we talk about recursion, it is the process in which each step of a pattern is dependent on the step or steps that come before it. So we just saw that in Koch's triangle. Sorry, Koch's snowflake. Now, a sequence is more of the numerical aspect of these patterns, is an ordered list of numbers. Okay, and usually when we talk about a sequence, usually it has some sort of pattern to it. Okay, but in general, any list of numbers can be considered a sequence. The sequences we're going to look at today are going to have definite patterns to them. So we'll come back to this in just a minute. Our first example talks about Heater King. Has parts for 2,000 water heaters. Um, It assembles 50 of them every day, gives 40 of them to the Mega Depot store, gives 10 of them to the small shop store. On day one, Mega Depot has 470, small shop has none. And we want to keep track of each store's inventory. So notice there are definite patterns here. Okay, so first of all, describe how the number of water heaters changes for each company. So we'll start off with the Heater King company. Now, to describe the number of water heaters each one has, notice we're going to have to include kind of two different things. We'll have to include how many they start with, because they all start with a different amount. And we'll also have to talk about how it changes. So, for instance, this Heater King company sells off 50 water heaters every day. So it decreases by 50 per day. So the sequence that's formed by this are the set of numbers 2000, 1950, 1900, and so on. So basically this pattern defines that sequence. Okay, now we can do the same thing with the other two. So Mega Depot obviously starts with 450, 470, but notice here they increase by 40 per day. And lastly, the small shop starts 0 and increases, we'll abbreviate here, by 10 per day. So again, each one of these little statements we wrote down here defines a set of numbers, defines a sequence of numbers is what we call. Okay, now going back, these sequences of numbers, these set of numbers, each number in that sequence is called a term. Now, each term also has an index that goes along with it. And it's an integer that indicates the position of the number in a list. When we don't know what that index is, we often use n. So that kind of represents what's known as the general term. Okay, the nth term of a sequence. Okay, so quick little short little example where we kind of use that little notation there. So if I give you 2, 4, 6, 8, or sorry, 4, 6, 8, 10, 12, 14, you'll notice that the pattern is increased by 2. That's pretty easy. Okay, now what we want is we're going to use a variable to name this list. So here I'm going to use u, and the general term would be known as u sub n. Okay, so 4 would be our u sub 1, 6 would be our u sub 2, 8 u sub 3, 10 is u sub 4, 12 is u sub 5, 14 is u sub 6. Okay, now obviously what is the recursive rule here? Well, the pattern is you start off with 4, you're increasing by 2 every time. That increasing by 2 statement is the recursive rule. It's the rule or equation that defines any term of a sequence in relation to the previous terms. So for instance, to get u sub 2, I took the one that came before it and I added 2. So that is the specific recursive rule. Now, the recursive formula kind of puts all this together. Okay, it defines a sequence. It gives the starting term or terms. We'll see an example that has more than one. And it also gives the recursive rule. And we're going to use our notation that we just mentioned to write our recursive formula. So for instance, in this quick little example here, I have to give my starting term. Well, what's my starting term in this sequence? It is 4. So I'm going to say u sub 1 equals 4. Okay, then I'm going to give the recursive rule, but I'm going to use the notation I just mentioned here. So to find any general term, our general term is u sub n. I'm going to take the term that comes before it. So again, to get the 6, we took 4 and we added 2. So the term that comes before this general term is going to be u sub n minus 1. And what are we doing to that term that comes before this when we are adding 2 to it? However, there's one more little thing you have to include. And you have to include the following statement. We can only use this recursive rule whenever my index is greater than or equal to 2 in this example. Now you might be asking, why do you have to include that? Why is that? Well, given this information, just strictly that information, ignore the rest of this. If I'm just given this recursive formula here, can I use that bottom statement to figure out what the term with an index of 1 is, the first term is? And the answer is no. You can use this recursive rule once you are given u sub 1 to figure out what u sub 2, 3, 4, and 5 is. That's what that n is greater than or equal to 2 represents. Now, going back to our previous example, now that we've recognized the patterns of these sequences, now we're going to go into writing recursive formulas for each one. So again, for each one of these, I'm going to use a different variable to name it. So for instance, in this first one, because it's heater king, I'm going to use h. And again, this was on the first day, so 2000 would be my h sub 1. So I'm going to start off with that. To get any general term, take the term that comes before it. And what are we doing? We're subtracting 50 in this example. And for heater king, this is whenever my index is greater than or equal to 2. For the next one, I know my first term is 470. To get any general term, take the one that comes before it. And here I'm going to add 40. And again, this is when n is greater than or equal to 2. Lastly, for the small shop, I'm going to use s this time to name the sequence. I know my first term is 0. To get any general term, take the term that comes before it. Excuse me. And you add 10. This is whenever n is greater than or equal to 2. All right, now we're going to start using these recursive formulas to do different things. I know that there are other formulas, and some of you might be itching and saying, oh, I know the other formula. There's a different way to figure this out. Yes, there is. However, we're going to be focusing on these recursive formulas for this chapter. Yes, we will come back and talk about what the other formulas are for each one of these sequences. But now we're going to use these recursive formulas to answer some of the following questions. For instance, how many water heaters will Small Shop have on day 30? If I tell you you have to use that recursive formula, you would sit there and go, all right, on the first day I have 0. On the next day I have 10. On the next day I have 20. And do this for 30 days. See where you end up. Well, our calculator is a nice little tool to help us doing that a little faster than sitting there and writing it all down. We're going to use our calculator to answer that question, and we're essentially going to use that recursive rule on our calculator. I'm going to start off with day 0, or on day 1, Small Shop had 0 heaters. So type in the first term, hit enter. Now, the little function we're going to use on our calculator is the answer key. So if you take a look right above that negative sign on your calculator, it says ANS. That is the answer key. So we're going to go second, answer. And Small Shop was adding on 10 water heaters every day. So I'm going to go plus 10. Now, notice what happens when I hit enter. It took the previous answer that is on the right-hand side of the calculator and it added 10 to it. So what I can actually do, which makes my calculator kind of nice, was this is day 1, 10 was day 2. If I just keep hitting enter, it'll give me the next terms. So day 3, 4, 5, 6, 7, 8, 9, 10. And you can continue. Now notice one downfall to this is that if you lose count, you gotta start over. Uh, so that so that is something to just be careful of. So I know Small Shop on day 30, because it's the 30th term of the sequence, is 290. Now we can do the exact same thing with the Heater King company. This time we'll start with 2000. So type in 2000 first. And now I want to subtract 50 every time. Now you do not have to go back and hit that answer key. If you're using one of the operations first, so for instance I'm going to be subtracting, it'll automatically put in that answer for me. So I'm going to subtract 50 and hit enter. So 2000 was my day 1, 1950 was my day 2. Just keep hitting enter. On day 15, so this would be H sub 15, we have 1300 heaters. Now the next question, to answer these questions, we're actually going to do the exact same process. So when will Heater King have less than 750 water heaters? Well, if I just pop my calculator back up, I want to see when will this number, okay, when will that 1300 keep going down below 750? Well, I'm on day 15, so I'm just going to keep going. Day 16, 17. Now you may have an inkling to say 26. However, notice it says less than 750, so I have to go one more. This is on the 27th day. Now I can do the exact same thing for the Mega Depot. When will it have more than 1,000? So again, Mega Depot started off with 470, added 40 every time. That 470 was day 1, 2, 3. On day 15. Now the last question on there is one that I'm giving you time to work on in class, so I'm not going to go through that exact answer. I want you to play with that and figure it out. The one thing I will say is the best way to do that is you want to basically keep track of each company at the same time. I would probably make yourself a table of values to help you do that. So for instance, you will find out if you do keep track of all the different companies that this occurs on, so cover your ears and your eyes if you haven't done this for yourself yet, day 27, and you find out it asks you for how many small shop has, so S sub 27 ends up being 260. All right, a couple quick notes about all these recursive formulas. First of all, is there a difference between, and again, u sub n minus 1 and u sub n minus 1? Well, notice where that minus 1 is. In the first part, it's in the subscript. In the second part, it's outside of the subscript. And yes, those are two different things. Okay, u sub n minus 1. Okay, the first one represents a previous term. U sub n, and then the minus 1 is outside the subscript, represents the kind of the general term minus 1 from its value. Okay, so notice those are two different things. Pay attention to where that minus 1 is, and make sure you put that minus 1 in the correct spot when you are writing formulas. Okay, next, within a recursive formula, make sure that you include a statement that indicates when the recursive rule can be used. So for instance, if I go back to this example, make sure you include that n is greater than or equal to 2. Now, it will not always be 2. Okay, it might not always be a greater than or equal to sign. Okay, it depends on the problem. You'll see a couple different examples in just a second. And lastly, u sub 1 will not always represent our starting value. It is the first term, but it is not always the starting value. Sometimes our starting value will be u sub 0, or maybe your starting value is something like u sub 5. Depends on the problem. And again, you'll see an example of that in just a second. Now lastly, the previous example we just did is an example of an arithmetic sequence. It's a sequence in which each term is equal to the previous term plus a constant. Okay, this constant is called the common difference. This sequence has a recursive rule of this form. Now, one thing I do want to point out is these are directly related to linear equations. We'll get more into this over time, but these things are directly related to linear equations. And lastly, if you're given a sequence and you want to know if it's arithmetic or not, think about how you figured out what the pattern here was. Okay, you notice it was going up by 2 every time. You would take any term, subtract the one that comes before it. That's 2. Well, if I take 12 minus 10, that's 2 as well. So that pattern continues. So in general, if you want to know if something's arithmetic, subtract any 2 consecutive terms. Any term minus the one that comes before it. If that difference is always the same, then it's an arithmetic sequence. If that difference is not always the same, then it is not arithmetic. And that should work for any consecutive pair of terms. Next example is just a little different. Okay, so we got a little pattern in geometry here. And first of all, it's defined recursively. So notice how you get from stage 1 to stage 2. You take any one of those black triangles and you cut out a little triangle on the inside. Okay, so this is actually a recursive pattern. This was Sierpinski's triangle that we mentioned before. Now it asks how many black triangles we have at stage 20. The first thing I do want to do, however, is write a recursive formula for this thing. So notice my starting term is at occurs at stage 0. So instead of using my starting term as something like t sub 1, I'm going to use t sub 0 here. My index is going to start at 0, and my term is 1. Okay, now your recursive rule that goes along with this. How do you get any general term? Well, notice what happens here. I have 1 triangle. I have 3 triangles. If you count them out, I have 9. If you count these out, you have 27, and that pattern continues here. Okay, so to get any term, take the previous term and make sure that minus 1 is in the subscript and multiply by 3. Now you always need that statement about when can you use this recursive rule. So this is whenever n is greater than or equal to, it's not going to be 2 here. Okay, it's actually, in this case, it's going to be 1. Okay, because notice you're going to use this recursive rule to find the first term, the second term, the third term. Because I started off with an index of 0, I'm going to use that recursive formula to find any term that has an index of 1 or greater. Now let's figure out how many triangles there are at stage 20. Again, I want you to use this recursive formula. Yes, there are other ways to do it, but for this chapter, we're using the recursive formula. Okay, we can do the exact same thing we did before. It's just here I'm using multiplication. Plug 1 into your calculator, then multiply your answer by 3. Now, again, that is the term with index of 0, index of 1. I want an index of 20, so this will be the 3 is the first term, second, third, fourth, fifth, sixth. And there is your answer. Okay, so notice how many triangles. It's a lot. 3,486,000. Oh, sorry, 3,486,784,401 triangles. Now, notice, is this arithmetic? Is the pattern arithmetic? No, it is not. This pattern has a different name. It is a geometric sequence, or it's a geometric pattern. Sequence in which each term is equal to the previous term multiplied by a constant. That constant is called the common ratio. And the sequence, these types of sequences always have this type of recursive rule. Now, if you're given a sequence, you want to find that common ratio. Instead of subtracting a pair of terms, you are going to divide a pair of terms. Last but not least, we're going to take a look at some. I'm going to throw some recursive formulas at you, see if you can figure out what they are. So, for instance, that first recursive formula is geometric. It's just like the Sierpinski's triangle one. So, describe the sequence. First of all, this one is geometric. Let's come up with 5 terms of the sequence. Notice this time I'm starting off with the 0 term, t sub 0. Now let's find 4 more. To find t sub 1, you multiply by 3. You get 24, 72, 216, 648. Notice the second one is going to be arithmetic. You are adding through every time. The big difference here is notice your starting term, it has an index of 2. Okay, so for instance, it just says find 5 terms, so I obviously have 7, then I'm adding 3 every time, and notice this is greater than 2. Well, that still works because our index is always an integer, and my integers after this, I can use this to find the 3rd term, the 4th term, the 5th term, and the 6th term, so that's still a valid recursive rule. So then 7, 10, 13, 16, 19. Now, could you use this recursive rule to find p sub 0 or p sub 1? And the answer is yeah, you could work your way backwards. So for instance, you'd have 4 and 1 if you needed to find p sub 0 and if you needed to find p sub 1. See over here, notice it's this time it's actually neither. You're not just adding, you're not just multiplying, you're actually doing 2 different things. And notice the rule is written just a little differently. First of all, they give me the first term, so that is the first term of my sequence. Okay, so they give me s sub 1, but notice this is written a little differently. It says take the general term, and if you want to find the next one, take the general term times 2, subtract 10, and that gives you the next term. So notice you can write these recursive rules just a little differently, using it kind of messing with those indices just a little bit. So for instance, if I want to find s sub 2, I'm going to put s sub 1 in for s sub n. 2 times 6 is 12, minus 10 is 2. S sub 3 would then be negative 6. S sub 4 would then be negative 22. And then S sub 5 would then be negative 54. Now, again, think about what that statement has to say. This is when n is greater than or equal to 1. Okay, so again, I can use this formula whenever my index is 1 or greater. So I'd start off by putting in s sub 1 to find s sub 2, plugging in s sub 2 to find s sub 3. So it'll give me this s sub n plus 1 can be used to find S sub 2, S sub 3, S sub 4. So make sure that matches that statement. Notice in D, you have, this is actually neither geometric or arithmetic. This is a different kind. And notice what that recursive rule says. To find any general term, take the one that comes before it and the one that comes before that and add them together. So when is the first time you can use that recursive rule? Whenever the index is greater than or equal to 3. So here I get two terms right away. Then I'm going to take those previous two terms and add them together to find the third, which would be 8. If I continue that same process, then my next term will be 13 and then 21. And last but not least, part E. It gives me, starts off with the starting term as k sub 0. So there's my starting term. Now, there's a little problem with this one. And hopefully you caught it. Okay, and it says to get the next term, or sorry, to get any general term, take the one that comes before it and add 8. But this only works whenever n is greater than 1. So can I use this to find k sub 1? Well, no, you can't. They don't tell you how to find k sub 1. So you can't go any further. You're done. You're stuck. You have to stop. Okay, so it's kind of almost an invalid recursive formula. It doesn't really get you that far because you can never find k sub 1 with that recursive formula. They would have to tell you how to find k sub 1. Here they do not tell me how to find k sub 1. So then I can't find k sub 2, k sub 3, k sub 4, and so on. But again, to reiterate, there are patterns everywhere in nature. Notice for that Romanesco and that fern, those are geometric patterns. However, there are other mathematical patterns that do exist, and some mathematical patterns that do have some really cool graphs. For instance, this graph that I have in the bottom center is called the Mandelbrot Set. Now, as I mentioned, there are different formulas for these patterns other than the ones we studied. However, for certain sequences, for certain patterns, for instance, in the Mandelbrot set, has a very nice recursive formula. But if you try to find a different formula that represents that sequence, it will be terribly difficult. It is horrendous. Okay, but that Mandelbrot set does have an interesting shape, and a shape that we have kind of seen throughout art history, as you see this ancient piece of artwork there. And what's also interesting about this Mandelbrot set is if you look at the graph of this sequence and you were to zoom in on a single portion of it. So for instance, along that kind of line that's on the top of the graph there, if you were to zoom in on that, if you zoom in far enough, you will see that exact same shape, which is kind of interesting. And this idea of recursion also appears in all sorts of current artwork, like stuff done by Escher and all those kind of interesting drawings that some people have hanging on their walls. And last but not least, Homer has your homework for today.